Okay, so welcome everyone to the second day of our random purification workshop. Today we're very excited to have a day full of channel learning. We're going to start with, I think, mostly upper bounds and Marco Fanizza. And I guess we're going to have a short break in the middle. We're going to continue with lower bounds.
Thank you very much, Angelos, and thanks to the organizer for this very nice opportunity. In fact, I will mostly speak about the construction of the random time spring superchannel, which has application for the upper bounds, and this is based on joint work with Filippo Girardi, Francesco Annamele, Jaime Zhao, and Ludovico Lami. And then, I guess the full picture on the upper and lower bounds will be then in next talk by Kim. Okay, so the outline of the talks is the following. I will first recall basic facts on quantum channels, dilations, and operations on channels, in particular super channels, so that we can define the problem that we wanted to solve in this work. Then I will show an existence proof for the time spring superchannel. I will show an efficient circuit implementation, and finally I will briefly discuss the application in learning and also an quantum information theory application, which is a Ullmann's theorem for channel divergences. Okay, let's start from scratch. So a quantum channel is a mathematical model for a transformation of a physical system, and mathematically is described as a map from matrices, dA times dA matrices to dB times dB matrices, that is linear. It is completely positive, meaning that if we apply the channel tensor, the identity map on an auxiliary register to a matrix which is positive semi-definite, you get a positive semi-definite matrix in return. And it's trace preserving. So the trace of phi rho is equal to the trace of rho. And CP and TP properties are the least you can ask for a physical map, because operationally they mean that if you act with a channel on a system and with the idle map on an auxiliary system, and you input possibly entangled quantum state, you get an entangled quantum state at the output. So that states are preserved by the evolutions. And you can think about this as a generalization of classical channels that you can described as conditional probability distributions, and this is the most general, extension to the quantum setting that retains a physical meaning. Okay, let's give some examples. So we have unitary channels that corresponds that also include reversible circuits that are used in quantum computation. So they act on states rho as U rho U dagger with U a unitary matrix. And a slight generalization of these are isometries, where the output space can be larger than the input space. And the action is still V rho V dagger, where V now is rectangular, and it's an isometry, meaning that V dagger V is equal to the identity in the input space. And intuitively, you can think about isometry as unitaries that are applied to a register where part of the register is initialized in a fixed pure state. And in this larger embedding, you have a unitary on the joint A system. And yes, and then we have also the partial trace, which generalizes the marginalization. This is a map that takes a matrix in the tensor product of matrix spaces, which then can be written as linear combination of tensor product of matrices. And the partial trace takes the trace of the right component in the tensor product. And the reason I brought up this example is that, in fact, every channel can be obtained as an isometry plus a partial trace. This is known as time spring dilation of a channel. And I think it's instructive for this talk to give a proof of this fact. So the way you get this is through Choi-Jamelkowski isomorphism. There is a correspondence between positive semi-definite matrices on a tensor product and completely positive maps between system A and system B. This isomorphism is implemented via a linear map that takes a channel and outputs channel tensor identity applied to the unnormalized maximal entangled state. And to go back to the channel having the choice state, you can use this formula here. That involves taking the partial trace of the choice state and identity tensor the transpose of the input. And so an important thing to check is what happens if you invert the Choi map starting from rank 1 states. And what you get by using this formula is this expression where you can then extract the matrix element of the input X, and they are sandwiched between these two matrices K and K dagger that one can construct from the vector V. And so for rank 1 states, the corresponding, or rank 1 operators, the corresponding channel has this form. It's Kx K dagger. But now for a general choice state, or a general, the output of the Choi isomorphism on a channel, this is a positive semi-definite. So one can also diagonalize it, and it will have non-negative eigenvalues. And via CJ isomorphism, the eigenvectors of this J of phi corresponds to map Ki rho Ki dagger. So this leads directly to what is known as the Krauss representation. You use the linearity of the Choi isomorphism to see that the channel can always be written in this form. And the trace preserving property is implemented by this normalization condition on the Krauss operators. And from the Krauss representation, one can get the Stein-Spring dilation via defining the isometry, the rectangular matrix V, obtaining by appending an additional register to the Krauss operators, which encode which Krauss operators you are applying. One can check that this is an isometry, and the channel can be written as partial trace, isometry followed by the partial trace. So the number R that appears in these sums is the rank of the Choi applied to the phi, and it's called Krauss rank. It corresponds to the minimum dimension of isometric dilation. And this is what generalizes the notion of rank for a state. And this completes the picture and allows us to define the kind of problem we want to address when we want to generalize the random purification for states to channel. So for states, we take as input n copies of the same state, and we want to generate an average of the same purification where a random unitary is applied to the purification register. While for noisy channels, the correspondence is that we want to take n uses of the channel and generates the channel that corresponds to the average over the unitary group of n access to the isometric dilations, where the same random unitary is applied to the dilation registers. And now the point is maybe, okay, so we knew what are valid operations at the state level. It's not so clear what are valid operations at the channel level. And the simplest thing you can do is to just consider linear maps that sends channels to channels. These are known as superchannels. And the very nice fact is proved by Chiribella, Deriano, and Perinotti, is that if a linear map sends channels to channels, then it can be implemented by a circuit. It is an encoding, possibly with an auxiliary memory register, and then a decoding. And mathematically, you can also encode the property of a linear map. So you can say that a linear map is a super channel if the map applied at the Choi level satisfies these two properties. It is completely positive, and sorry, here there should be a star. And it preserves a certain partial trace condition. So it sends matrices that have a partial trace over B equal to kappa k times identity to to output that has the same property for the output for the new input and output systems. So this is really just the translation of sending channels to channels, but if you look at the linear map at the level of the Choi isomorphism, which is itself a linear map. And okay, so if you have many copies of the channels, then more complicated structures emerge. And these have been studied as higher order transformations. They can have various type of causal structures or even don't have a causal structure. The most general setting with causal structure is called quantum comms. They allow for considering sequential strategies where the output of a channel is processed and then sent as input to another query to the, of the channel. But in our work, we only focus on the simplest setting, which is the parallel setting, where we think phi tensor n as just a big channel on a larger input system. And we think about superchannels, transforming these big channels. So there is no sequential strategy allowed. Okay, and now I'm ready to show you the existence proof. And the existence proof is actually very simple. It's just based on Choi isomorphism and the fact that there is a random purification channel. So this is actually, I mean, I'm showing you the proof with the purification channels that have that works for maximum rank for now, and then I will show that actually this can also be implemented with the Krauss rank that is tailored. So for so we define a map acting on Choi state as the random purification channel on the Choi state. And by Choi isomorphism, we can then see what this map does at the level of the channels. So we define S star on the Choi state. And then what is S applied to phi tensor n, evaluated on an input row? Well, then you use the formula for getting the output of the channel from the Choi state. But the Choi state, by definition, is just the purification of the Choi state of the channel, a random purification of the Choi state of the channel. And now, this is in fact, you can see that this corresponds to the average, random average on the dilation register of some isometric dilation of the channel. And then via the transpose trick, you can bring this rho transpose A prime to the register A, and what you'll find is exactly what you want. So this this super channel, or well, this conjecture super channel applied to phi tensor n and evaluated on input row, it takes input row, it applies the random isometry, where we just randomize over the dilation register, and that's what corresponds to the to the random Stein-Spring dilation. Questions?
Was it surprising to you that it was like so clean?
Yes.
Did you guys just expect it?
No, I don't think we have to when I after the fact, it's always surprising that it's nice that it's clean, and you would have say, I should have guessed, but yeah, it was not that obvious at the beginning. Maybe because we didn't work too much with super channels, so yeah.
Sort of a simple question. I just want to make sure I'm following. So the idea here is that you get n copies of a channel, and by wrapping it with some circuitry on both sides,
right,
you convert it to something that adds some qubits, does n copies of the unitary, possibly a randomly chosen unitary, and then traces out some stuff at the end.
The trace is okay. So here it is the picture. I'm right. So you have the same input space. Yeah. The output space is dilated.
Right. You
don't trace out.
Well, you could trace out.
You could trace it. If you trace out, it's you get back to what you had at the beginning.
So at the highest level, it's you can convert a channel to a unitary channel.
Yeah, isometry, yes. No, but not to a unitary, because...
Well, a unitary in a bigger space.
Yeah, but you cannot access the input, the full
It's
input.
actually not possible to do the unitary.
Okay, fine, I saw what you mean.
Yeah,
You mentioned to Francesco at some point, right?
I think so.
Yeah.
I thought someone had. Well, I think it's also the case that like if I could get access to the unitary, then you could use it to solve. When I have access to unitaries, you can solve things with like a Heisenberg. What's it called, the Heisenberg limit, where like things only take 1 over epsilon queries rather than 1 over epsilon squared. But there's some things with channels that you should only be able to do with 1 over epsilon squared. So there should be some sort of loss, I think, when going from the channel to a unitary, at least like a quadratic loss. Whereas going to the isometry, you can just do like n queries of 1 instead of n queries.
Thanks. Yes, but yeah, the proof is not finished. This is only showing that the linear map works. You have to show that it is a super channel. Well, of course, it's CP. That is clear because it's implemented by the purification channel, which is CP. And then you have to check that it preserves the partial trace condition. And this works as follows. So you take the trace of BEN EN of S applied to X. And then this corresponds to purifying channel applied to X. But now for free, you can put an average of over the permutations because the purification superchannel symmetrizes the states. And then, but then for the purification channel applied to symmetrized states is an extension of the state. So if you trace out EN, you get back the symmetrized one. And now this is acting with the same permutation on registers A and B, but now in the partial trace, the permutation is on B, that cancels. So you're left just with the permutation on A, partial trace of B of X, which is cap K times identity, and the average permutation is a unitary channel, a unital channel. So you get K identity. So the partial trace condition is satisfied. So this is actually a super channel. So let me mention also related work in this direction. So Chen, Yu, and Zhang with the local tester method show the constructions of measurements that taken a tester gives you a tester that simulates access to dilations, and their construction suggests the existence of the Steinspring superchannel. One can see this as a dual construction at the level of the observables rather than the channels. And then just after the day after our work was put on the archive, also Yoshida, Niwa, and Murao showed independent proof of existence of the channel and the circuit for the channel, and also applications. And see also the second version of this with Utsumi and Takagi, where they also consider sequential strategy. Okay, so what the proof of existence shows is that one can find an encoding and a decoding map that implements the superchannel, and just by reverse engineering Kiribella, Dariano, and Perinotti's proof, one could get an expression for those. But this is not so interpretable, and also it's not clear how to get an efficient circuit. So we had to find a circuit, and this is it. So this is in fact a circuit that implements the superchannel with an R-dimensional dilation, where R, so that it dilates all the channels with cross rank up to R. And while you look at this picture, let me comment briefly on the building blocks. Here we have quantum Fourier transforms for the symmetric group. So this register here is hosts permutations. Like the basis states are labeled by permutations. So with these basis states, you can do control permutations on the input and output systems. And then the last part involves preparing maximal in mixed states on a UD irrep and then the Schur transform. These already appeared in the circuit in the works that were presented yesterday. So I will not give a lot of details on this part and mostly focus on the QFT and why it works and why maybe it's also a very nice way to think about the state purification channel.
Can I ask, like, so to show the existence, all you needed was the existence of the random purification channel. So, like, if I gave you a circuit for the random purification channel, like, could you just black box some parts of this, or do you really have to design a circuit from scratch?
No, that's very interesting, but it depends on which circuit, and that's a very interesting question, and you will have the answer in a few moments. It depends on the circuit, though, to understand if you get an efficient one. And okay, so let me tell you something about the QFT. So the space where this acts is the space that was the regular representation of Sn. The basis vectors are labeled by permutation, so the dimension is n factorial. Here there is a left regular representation where sigma acts on tau as sigma tau. And right regular representation sigma acts as tau sigma minus 1. And so they commute, and you have a representation of Sn times Sn. Sigma prime acts as sigma tau sigma prime minus 1. And so if you decompose the representation of this direct product into irreducible, what you find is this decomposition where the irrep are labeled by partitions of n, and they appears in pair with the same label. So you have an alternative basis for this space, which is given by partitions. Pictorially, you can think about that if you know about this as Young diagrams. And then I and J are indexes for the basis of the irreps, and this can all be embedded in a larger tensor product form, a register, where you have an irrep label lambda, standard Young tableau on the first register, standard Young tableaus on the second register. This, I will not say how standard Young tableau works, but it's just an encoding for these basis vectors. And now what the quantum Fourier transform does is takes permutations and generates a linear combination in the new irrep basis, in the irrep theory basis, where the coefficients can be thought as Fourier coefficients of sigma. These are the matrix entries of the irrep lambda evaluated on sigma, and then there are some weights to ensure unitarity. And okay, if you want to actually implement this in a circuit, you have to think of this as an isometry if you want to get this tensor product structure at the output. And then what is nice is that you can produce the coherent superposition of permutation by applying the adjoint of the QFT to the state that corresponds to the invariant representation. Okay, the other piece that appears is the Schur transform, and this is a circuit implementing a change of basis that realizes Schur-Weil duality. So n copies of a system of dimension D host a representation of permutations and unitaries, and the reduction into irreducible have this form, where again irrep appear with labels that are identified with the partitions. And multi-copy states have a peculiar form. They are block diagonal in this decomposition. They look like the identity on the permutation register as they commute with permutations, and something non-trivial on the UD register. And now, of course, if the input space is trivial, the input space of your channel is trivial, then what you get is just a state. So this super channel should also work as a quantum purification channel when phi is just a state. And this is what happens. So basically, I want to spend some time in describing how this works, because this is then the basis for doing the computations also for the channel case. And so this line here, imaginary line here, represents a division between, if you know how the circuit works in the original presentation, So up to here, you have done weak Schur sampling, that is measuring this lambda in the Schur-Weyl duality, and prepared an EPR pair.
Sorry, what is C1?
Control permutations.
Control permutation.
Yes. So here you have permutations and you can control. Okay, so where does this circuit come from? Not surprisingly from Aramaro's thesis. So what he considered there was to use this setup to do an alternative circuit for weak Schur sampling, just sampling this irreplaceable lambda. And this can be seen as a non-abelian version of Kitaev's phase estimation can be used in Shor's algorithm, for example. And it looks exotic, but for the special case n equal 2, this is just a swap test. And what Arrows did was to trash both SYT registers here. But if you trash partial trace just one of them, you get something very interesting. So let's see how this works. So you take rho tensor n, which has this decomposition according to Schur-Weyl duality. Then you take partial trace over SYT, say, second register of the QFT applied to what you find here. And this is just, we said that the output of this blue block is just a coherent superposition, uniform coherent superposition of permutations. So you get that this coherent superposition controls permutations on rho tensor n. But now permutations commute with rho tensor n, so you can collect this in a unique permutation. And QFT plus tracing out a register effectively gives you a contraction between Fourier coefficients, between the IREP matrices, so that you end up with R lambda, the matrix IREP lambda, evaluated also on sigma times 1. And now, if you write rho tensor n in this way, you can separate the register where permutation acts and the register we have rho lambda prime. So you get two permutation registers, and U sigma time minus prime just acts as said by Schur-Weyl duality as the IREP R lambda prime in that sector. And now this, the brace should extend up to here. So this is then, you can see it as just the average over the action of the permutation group, which is projecting on the invariant subspace of the tensor product of two IREPs. And now if lambda and lambda prime are different, this is just 0, and if they are equal, then this is just projecting on the invariant representation, which corresponds to the EPR pair. It's the unique invariant state. So that's why you can prepare, you can measure lambda and prepare the EPR pair in one shot with the circuit. Okay, now for the channels, what we did, maybe naively, yes.
Was that supposed to, at the end, what you get is supposed to be the output of the random purification channel? Is that right? Or?
So at this point is still the first part of the random purification where you still have to add, the unitary part.
Okay.
Yes. Yeah, that part we didn't change. And then for the Steinspring dilation, so I was saying that naively we just did the computation. So we took what the Steinspring dilation does, evaluated a certain expression with Weingarten calculus that does not involve any specific dilation, but just the channel tensor n and permutations. You can get this by using identities on integrals of our random matrices. And then, by calculation similar to the ones that I showed before, one can also get this expression for the circuit that we designed. And now this highlighted part can be shown to match by looking at how permutations act in the Schur-Weyl basis. So once you show that this match, then you have shown that you have implemented the superchannel. But yeah, don't stare at this too long, because Yoshida and the other and the co-authors have found, in fact, a much better a way to to explain why this works. That is, after fact is also neat and intuitive, and this answers the questions that John said. Because you can, once you have the circuit, you can see what it does at the level of choice state of the channel. So if you look at the choice states of the output of the super channel, you see that it takes this blue control permutations by transpose trick can just be sent on the other side. And now what we have here is the random purification of the choice state of the channel. So exactly because you had this control operation in this original circuit, then you can prove this identity in this slick way. You have to prove, though, that this is a random purification circuit. And that requires you, again, to see the calculation that I showed before with the QFT.
Can I also ask, like, for the random purification channel, there's like, when you consider general n copies, you have to invoke all this rep theory. But when it's just one copy, it just like turns out all you're doing is depending on maximally mixed state.
Yes.
Is there something similar?
Yeah, exactly. And also for 2 copies, we had the circuit based on the swap test. And that's also why we thought about the QFT. Because if the irrep space are trivial, just one-dimensional, then it's very easy.
Well, if it's just one copy, is it literally just like depending on maximally mixed state?
Yeah.
Or something like that? Or?
Yeah, we write it down at some point. But yeah, it's very simple. Yeah, it doesn't require. So yeah, the output. Anyway, you do the twirling on the output. So yes, it's that. It's just need to append the maximal mixed state. And but also with 2 copies is easy, because the dimensions of the irreps are just one-dimensional. So there you don't need the full QFT machinery. It's just a swap test. And okay, so I think it's also nice to spend some words on more detail on the efficiency of the circuit. So for the generalized phase estimations, you have to encode the various bases in a certain way to get efficiency. Say, you have to encode partitions, you have to encode standard Young tableau, and also permutations. So this is a very nice way of encoding permutations. Permutations can be written as I1 powers of 2 cycles, 1, 2, I2 powers of 1, 2, 3, and so on. And these encodings were used in the version of the QFT by Kagawano and Sekigawa that improved on the original Bill's circuit. That shows that the QFT can be done in poly-n time. And then also control permutations with this encoding can be shown to be efficient. There are a lot of permutations. So in principle, it's not clear to see that this control permutation is efficient, but with this encoding, it is. And maybe we can talk about it if you are interested. So the other important block is the Schur transform. This was introduced by Bacon, Chuang, and Haro, and the state of the art is now given by a paper that appeared last year. The encodings here for lambdas and Young-Yamanouchi basis standard Young tableau are compatible with the QFT. You also need a way to encode Gelfand settling patterns for the UD part. In fact, they do it in a compressed way. So you have a picture here of a GT pattern, but they use a more refined way of encoding. And they show that the circuit complexity is polynomial in n, log d, and log 1 over epsilon. One should also be a bit careful with the fact that you are encoding this is the valid vectors in Schur-Weyl duality in a big space, which is tensor product of 3 registers. And it's not clear that all basis vectors occupy, say, the first registers in the computational basis of this encoding. This was, Elias Tail made me notice this, and also I communicated to others. This is important for efficient preparations of EPR pairs and maximally mixed state. And as far as I understand in this new paper, this is not very well discussed. But in fact, there is consensus that it is possible to encode well to do this encoding such that you can have an efficient mapping between numbers, like from 1 to the numbers to the dimension of the irrep that you care about, to the first bit strings in a computational basis. To that and so that you can map this efficiently to the bit strings encoding standard Young tableau and GT patterns, and this is related to a combinatorial problem that is known as unranking. And the sketch is already in our thesis, but it's not yet explicit for GT patterns.
These are bijections between all the objects, like numbers and correctly encoded bit strings and.
What do you mean bijection? So you are in a larger space in principle, but you can have a compressed encoding.
Well, there's like a unique encoding for every irrep.
Yeah, it's like there's an efficient map that takes you from like 1 to dim lambda that maps those numbers into SYTs.
But SYTs are separated. Like there is some information that tells also in which irrep you are, so you don't mix them up.
But you also have like unique bit string for every SYT. I guess.
I think you don't want that. You want to encode that everything in the first bit string. Like you're not. Yeah, I think you don't want to have some qubits for one irrep, some qubits for another irrep, right? I think you do it after you know lambda. You can do this efficient mapping. Oops. Okay. And okay, but then it was also nice to observe that there is an alternative way of doing this preparation of maximally mixed state in the UD irrep that doesn't use this unranking, and it's with random circuits. Because there, if you take a valid GT pattern and standard Young tableau, you can apply the Schur transform and then apply a layer of random Haar unitaries, and this will implement the twirling, so it will send any state into the maximally mixed state. You can then trash out, in the UD register, of course. You can trash out the standard Young tableau that you don't need, and you get what you wish. This is if you had an exact Haar random distribution, but you can produce n designs with the epsilon down norm error in-depth polylog and log D. Thanks to the paper by Schuster, Haferkamp, and Huang. And this is enough for our purpose to get a circuit that is accurate at diamond norm error, epsilon. Okay. I have how much time I have? 15? Okay. So yes, let me then talk about the applications. So yeah, it's maybe also good to just properly introduce the diamond norm distance that is used in the learning results. So this is one of the most natural metrics on channels, and it's the one induced by the trace distance of output of entangled states. So the diamond norm of the channel has this expression, and the distance, you can think about it as the maximum trace distance between outputs of the channels when you optimize over both the dimension of the auxiliary register and the input states. And this is related to the probability of error of optimally distinguishing two channels with any experiments allowed by quantum theory. Then one can also consider generalizations for every divergence between states. One can then define a divergence between channels by a similar process. So you take any dilation register and you take the sup over any states that live in the system of input space and auxiliary register. You apply the channel tensor identity to these states and the other channels, and then you take the divergence between the resulting states. And the examples for this, example of divergences are the omega k relative entropy or minus the log fidelity. Okay, so let's focus for now on the diamond norm, and let's look at the applications of the Stein-Spring superchannel in learning. So what is clear is that the existence of the superchannel shows that channel learning with parallel access reduces to parallel isometry learning. And the same way as mixed state learning reduces to pure state learning. And there have been a sequence of works that I want to mention that allowed us to understand sample complexity for this task. So the first paper that I want to mention is by Ha, Kotari, O'Donnell, and Tang, where they did learning unitary channels in d square over epsilon square queries, parallel queries, and this then can be boosted to d square over epsilon adaptively. And then after the random purification channel construction came out, Mele and Bittel found a way to use it applied to the choice state of the channel to find efficient way to learn channels with RDADB epsilon square copies. R, I recall it's the Krauss rank. And this also specializes to isometries. And their computation is not just, they have to do something specific for general choice states. They have to study well the output distribution of the measurements. You cannot get to this result just by naive the naive error propagation from trace distance to diamond norm distance. But then in the paper by Chen, Yu, and Zhang, they also gave another way of learning isometries by directly extending HKOT. And with the local tester method, they get this result. So the same result at Mele-Bittel by using the Stein-Spring dilation. Because now the output of an isometry will be R times dB. So it's really, but yeah, there are some differences in terms of the probability of error dependence. But both methods get to the same dependence on the dimension. And yes, so with our construction, one can use one of these results also to recover the same. And very recently, a few days ago, there was a new paper by Haley, Scully, Zhao, and Yang that showed that Eisenberg scaling is possible in the parallel setting too, with d square dependence. And this means that via Stein-Spring dilation, we can get also Eisenberg scaling for some channels that are not unitaries. As soon as the RDA is equal to dB, so that the dilation is a unitary, not just an isometry. Yeah, this happens when you have output spaces that are small with respect to the input space. I think it's a very interesting regime to study channels in the setting, because it's like, okay, if you want to understand what Boolean function do, so Boolean functions, for example, is large. You want the input register to be large, the output is just a bit. And so studying channels in this regime where the input is large and the output is small, it's an interesting problem, I think. And Keen will tell you more about this. Okay, then the quantum information theory applications. This is a generalization of the property of the fidelity that you can get the fidelity between two states by maximizing the fidelities of purifications of the states. And for the minus log fidelity, you minimize. And so this in the paper on the random purification channel made simple, Girardi, Mele, and Lamy found a concise proof for a generalized Ullmann's theorem for divergences that is more general than just the fidelity, and using the random purification channel. There were already other proofs of this, but there was no proof for channels yet.
Sorry, the thing that makes it a generalized loop theorem is just that it's not just for fidelity,
Exactly.
but it's a general divergence.
Yes.
So it's like not this.
Yeah. It's for not for all divergences. They have to have some properties.
Right, but are those like precisely the properties that other proofs would get to, or are there some divergences where
Yeah, no, I
it's
think
known to satisfy this property, but or
no.
it's
Also,
known-
yeah, this property was also used in the other proof. Yeah, the most important thing is what's called the weak quasi-concavity. I will show it. So yeah, okay. So a divergence is a measure of distance between channels that satisfies data processing. And then one can also ask the property that the divergence is jointly convex if the divergence of convex combination of rho I and sigma I with the same weights is less than the convex combination of the divergences between rho I and sigma I. And in fact, joint convexity is a consequence of the data processing inequality whenever the divergence behaves well with respect to classical quantum states. That it means that it sends this mixture of pi, ket I, ket bra I, rho I, and the same for sigma in just the sum, so the average of the divergences. And most divergences of interest have this property. So they also satisfy satisfy joint convexity. Then, so what are good divergences for channels? You can define them directly from state divergences, but usually you get non-additive measures that usually they do not have operational significance. What does it mean to be non-additive? It means that if you take the divergence of tensor products of channels, like pairs of tensor products of channels, this is not the sum of the divergences. This is what you would have at the level of states, but not necessarily the level of channels. So what you look at are then additive regularizations, where you take the lim-inf of 1 over n times the divergence between many copies of the channels. And in Ullmann's theorem, then you want to compare this object to the related objects in terms of dilations of the channels. So you want to compare it with the divergence between a dilation, fixed dilation m bar of m, and all possible dilations of n with the same input output. And the way you define this regularized divergence with respect to a set is by taking the lim-inf of 1 over n, then you take the inf over all possible dilations of multi-axis channels. So these are not necessarily tensor product. And of the divergence between the multi-copy axis to the dilation m, and then this general dilation n bar. So what is the role? The proof is a bit complicated. I want to highlight what is the role of the Stein-Spring superchannel here. So one direction is obvious. So the divergence of n axis to two channels of a pair of channels is less than the divergence of the two dilations, just by data processing. But then the other direction is where the Stein-Spring superchannels appears. It's because you can always lower bound the divergence between m tensor n and n tensor n by introducing, which is written in this way, by introducing the encoding and the decoding map. They will only lower the distinguishability of the two channels. But now encoding and decoding map will implement the Stein-Spring superchannel. So you see that now the isometry has appeared. And now you want to get rid of this expectation value here to get a specific dilation of m. And this expectation value here is not a big problem because here you are considering all possible dilations. And then that's why you use these other properties, that is that the divergence is not only jointly convex but also weak quasi-concave, so something that goes in the other direction. Many divergences satisfy these properties, so it means that the divergence between a mixture, so the convex combination of rho I and sigma is larger than the minimum of the divergence rho I sigma, and a correction that is a logarithm of a polynomial that can depend on the dimension in the number of components in the mixture and in the size of the spectrum of sigma. Yeah, I won't tell you why this is true for most divergences. It's something that we can just assume. And if this is true, then we have the equality. And I can give you some ideas on the proofs. So this uses the previous data processing inequalities that I showed. The fact that is joint convexity tells us that we can maximize over pure states, and then to control n and the size of the spectrum, one can use Karato-Lewis theorem applied to multi-copy choice states, which span a space that like a subspace and a set of that is not too large. And this allows to bound both n and the spectrum of sigma when you input a pure state into an isometry, and then you take the average of a random unitary on the dilation. Yeah, if you want to know more, feel free to ask. And so, yes, I'm almost at the end. Maybe last slide, I want to mention open questions. In these directions, there has been work on purification channels for general symmetries, and now it's natural to ask what happens for the Stein spring superchannel, and in particular for bosons and for fermions, how would this work, and of course also whether there are efficient circuits. For now, we don't have nice transforms for these other symmetries, and this is a very interesting problem. It's also very interesting to look at optimal sequential implementations, maybe approximate. I didn't tell you about the recent results in the V2 by Yoshida et al., but the problem is still open in some sense. It's natural to ask if there are other Shannon theory or resource theory applications because just inspired by the example with the Hullman's theorem. And then for learning, one can ask how can improve upper bounds on isometry learning. There is a full range of parameters. There are matching upper and lower bounds for certain regions of parameters. And this covers the worst cases, but there are also other regions where we don't know what to do. And of course, if you improve isometry learning protocols, you can upgrade them to channel learning protocols via the Stein spring dilations. And another question is, what about coherent quantum inference for channels, information processing with the unknown channels? Can you have applications of the Stein spring superchannels there? And with that, I finished, and thank you for the attention.
So this implements, I guess, 4 queries to dilations. Have you thought about is it easy to use your technique to implement inverse queries or linear queries?
How do you do it for channels now? So you would like to implement what? It's like here there is no unitary, so it's an isometry. You want to implement the adjoint.
I guess if in the case where it's unitary, let's say, like where the uniform.
I think you can chain it with other works, right? But I don't know about the optimal. So if you know a way of getting the adjoint from copies of parallel isometries, then you can just chain it with the Stein spring superchannel. But it's not something I thought about. Do you know?
Yeah.
Okay.
you comment on the possibility to do sequential purification, like purify the channel with all sequential?
Yeah, I wish I knew more. So there is a no-go theorem for a certain kind of sequential purification, sequential dilation in the new version of Yoshida et al. And they also implement a kind of sequential dilation using the controlization procedure. When you get access to parallel isometries and you want to get controlled version of them. I think, yeah, that's what I didn't read the paper very carefully, but I think that's
There's
what
like, there's like a task where I think it's like if I'm given access to if I want to apply it sequentially, and if I'm given access to like a dilation, then I can do it in like one query or two queries maybe for the channel. But if I'm not given access to a dilation, I require like exponentially many queries. They're saying there's some setting in which they can do it.
I think they are using your construction. Yeah, maybe we can look at it later. That makes sense. Yeah, you can use the fact that you have many copies of the dilation. They have to have an override. They don't do it with the same number of copies.
All right, let's thank Mark again.
Thank you.